Okay, so I wrote down here in the blackboards some references. This first reference is a physical report. It is about Bartolini-Wilkowiski formalisms or fields anti-field formalisms. And this report is very nice because actually introduce first gauge symmetry, then BRST symmetry, then fields anti-field formalisms, and you see all very nice examples applied to particle gauge theories, Chern-Simons theory, even string field theory is also discussed in this reference. Okay, so there are a lot of information in this reports. These two papers actually are two introduction to BRST symmetry and gauge theories, some lectures given by Carlo Becchi in some schools, and there you also find some references regarding the geometrical interpretation of BRST symmetry. I think you can search, for example, for references given in these two papers or in the physics reports. There is another physics report actually, which is a little bit later, I think 97, 98, by Barnik, Brandt, and Eno. That is the title is I think local BRST cohomology. I will give you the number next time, which is more about the calculation of BRST cohomology. I will introduce this subject in a moment. Okay, so I will try to recapitulate what I did last time, and then we move to non-abelian case. Okay, so last time what we did, we started from a gauge invariant theory. So we have the gauge symmetry, that's for the abelian case. We have also the field strength for the abelian case. And then we have the Lagrangian, which is the invariant Lagrangian for this abelian case. And then we discussed that in order to quantize this model, we need to, first of all, to fermionize the symmetry, and it becomes a BRST symmetry. And then here introduce the Gauss field. Okay. Then the second step is adding an S is equal to 0, in such a way that this differential operator S square is equal to 0. And then we add a non-minimal sector. In this case, it was rather easy. It was an anti-Gauss and a Lagrange multiplier of this type. And then finally, we add the gauge fixing. In such a way, the gauge fix action is just a sum of a gauge invariant action plus S of something, which I wrote in this way. In general, I wrote it in this way, where this is the gauge parameter. The gauge parameters. Okay. So this is gauge invariant part, and this is BRST exact. BRST exact. Of course, I can always add something which is BRST exact in such a way that the final Lagrangian, the gauge fixed Lagrangian, it is BRST closed. Okay. Good. So this was the situation for Maxwell theory. Then, in order to move to Yang-Mills theory, okay, so we have to do some small changes. First of all, the gauge symmetry for the abelian gauge theories was this one, okay, which I rewrite in this way. So it's derivative of lambda plus I of g, and here I just add the Lie algebra commutator. Do you remember? You remember that A and lambda they have values in the Lie algebra of the Lie group. Okay, so this bracket here is just the Lie algebra bracket. And then so also we have the field strength, which also the same structures, but in addition there is one additional terms, which is just these non-linear terms in the field strength. And then we have the action again, so the invariant action, which is minus half of trace of f mu nu, f mu nu. And we know that this action is invariant under the gauge symmetry. So then we did this. We do the same game. So first we fermionize the gauge parameters. So and then we write down the gauge symmetry in this way. So it's d mu of c plus I of g of a mu c. Okay. So I added the Gauss again, but the Gauss again has a value in the same Lie algebra. So as the Gauss C has the value in the Lie algebra. And then we checked last time that in order that this operator S is nilpotent, okay, in order to do that, we need a non-trivial transformation for this. So S of C is equal to minus half. And then here I can write down this way, C, okay. Last time I wrote it with just indices, which is just minus half F B C A C B C C in this way. But you can write down also using the commutators here. You remember that actually when you have a commutator, it probably, yeah, I think if you write down the commutators, it happens the following. So you have a CA, so C, CB, gosh. So I can write down like a CA, TA, CB, CB, TB, okay. And then I can, of course, I can take out this C from this CA and CB, and then here the commutator CTB, okay. And then, okay, this is it's a meaningful expression because this is anti-commuting variables. So therefore, if I exchange these two C's, okay, I get a minus sign, but also there's a commutator here, so it is perfectly well-defined equation. And then for this, I can use the algebra. So I have I, F, A, B, C, T, C, and then I get back to the equation in component. So for each component of the Gauss C, I have the following equations. So then, of course, this is not yet finished. So I've that S square on A is equal to 0. So the BRST operator, the BRST variation on the gauge field is 0. But then I also have to check if S square is C is also 0. Okay. There are two ways to do it. One way is by using this formula with the component. If I do S square this, I have to act on this and this. So when you do that, CA, I get minus half FBCA. Then the first one give S of CB, CC. But then when I go through, okay, so this is an anti-derivations. So if I go through one of the Gauss, I get a minus sign. I get a minus CB S of CC. Okay, then I apply again the same formula, okay, and then I use the Jacobi identities for F, which is like F, B, C, F, C, D, E, and then you anti-symmetrize. So this symbols means that you anti-symmetrize on this index A, B, and D. You don't touch C, okay? And the C is summed. So C is summed, E is free, so this is summed like this way, and A, B, C, A, B, D are anti-symmetrized, okay? So these are the Jacobi identities for the structure constants of the Lie algebra. Okay, so if you use these equations, then automatically you check that S square to 0 also for the Gauss. Of course, you can also use this formula to do the same game. So if you do S of C is equal to minus half, and then again I have S of C times C. Then I go through, which is so it's a plus half. Then I get C and S of C in this way, and then here I replace the same formula, so I get a minus half. So I get minus half of C wedge C, C. The same things here, in this way. And then you see that you get this double commutator, so you get C, C, and C, okay? But this actually is equal to 0, because if you do this, if you write down these double commutators, so first you pull out 2 C's, and then there's a third C, but those are totally antisymmetric in the indices A, B, C, and so this gives you the antisymmetrization of the indices for 2 structure constants. So you get one structure constant coming from this commutator, you get one structure constant coming from this commutator, and then you have to antisymmetrize all the indices, and then because of the Jacobi identities, this expression vanishes. Okay, so in one way, so let's say written in this way, you need to play with the indices. If you write down in terms of just Lie algebra commutator, you just need the Jacobi identities in this formula. Essentially, this expression here encodes completely the Jacobi identities. I mean, the fermionizations of the gauge parameters using some Gauss, okay, or let's say, which is also known in the literature as the fermionization of the Lie algebra, allows you to write down the Jacobi identity in a very compact way. It's just this one. Also, in some books, actually, you instead of writing in this way, some people write down like a C, where you see write directly as a C square. Okay, I found a little bit minimal expressions, but actually, in some books you find also this expression altogether. And the double commutator is just a C cube. But anyway, so I'm not going to use it. Okay, so, but in some books you also find this notation. So then the last bit we need is now to add in the nominima sector. Okay, so adding the nominima sector is the same as in the abelian case. I introduce another Gauss, C bar, and this also has values in the Lie algebra, and together with the Lagrange multiplier, both has values in the Lie algebra, in the same representation as the gauge field and the other Gauss. And they transform in this way: S of C bar is equal to rho, and S of rho is equal to 0. Of course, if I'm going to write down in component, S of C has one index in the component of the given representation, and rho A, S of rho A is equal to 0. So this is written in terms of object which value in the Lie algebra. These are written directly in component. And then you see immediately, this equation is automatically, as this is written in this way, it is automatically S square of CA is equal to 0, and S square of rho is equal to 0. So it just playing the same game. So the only difference is coming from the non-abelian part here. So you need these additional equations. And then for the nominima sector works exactly as in the abelian case. So now what about the gauge fixing? Okay, let's do the gauge fixing now. Okay, so in order to do the gauge fixing, I do the same game. So the gauge fix action is just the gauge invariant one, okay, plus S of something, okay, S of something, and here I write down in this way: C of A, right? Let me write down in this way: trace of C of A. And here, just to put the same things as in the case of the abelian gauge. Let's first do it in the Landau-Fermi gauge. Okay. Now you see, these two objects has a value in the Lie algebra. Okay. So therefore, I need the trace in order to be invariant under the rigid symmetry, at least. Okay. Of course, this is not invariant under the gauge symmetry, because the divergence of the gauge potential, it is not invariant under the gauge symmetry. So this manifestly break the gauge symmetry. Okay. But then, since I wrote it in this way, like S of something, the full action here, the resulting action, will be BRST invariant, because this guy is gauge invariant and automatically is also BRST invariant. But this guy is BRST exact, and so therefore it is not gauge invariant, but it is BRST invariant. There is one observation, okay, that I have to do before going on. Okay, so we have the following set of fields. We have the gauge field. We have the Gauss C, the Gauss C bar, and the Lagrange multiplier rho. Okay. Now you can check, for example, two things. What are the dimensions of those fields? I'm working in 4 dimensions, okay? So the dimension of these fields is 1 here, okay? Now actually you see that the BRST variations map a gauge field into C, but here there is a derivative. Now there is 2 ways. One way is the following, okay, is to assign a dimension 0 to the Gauss, okay, and dimension 1 to the derivatives, okay, or you assign dimension 1 to the BRST differentials in such a way that this has a dimension 1 and this also has a dimension 1, okay. There are these 2 choices, okay. In some cases the choices let's say is important. In some cases is unimportant. It is important when actually no, first of all, let me tell you, it is unimportant, so it doesn't really matter if you have only massless fields, massless degrees of freedom. For example, if you have photons or massless gluon, this works perfectly, or massless quarks, everything works perfectly. However, when you have a massless and massive particles, then it's a little bit more delicate, okay. Namely, sometimes it's better to keep this as dimensionless parameters, okay, and the BRST operator dimensionless transformation, or in other case it's better to use this as a dimension full parameter, and the BRST transformation it has dimension 1, okay. It's a matter of how you regularize the theory, okay, but so for the moment I'll keep it dimension 1, this one, and also dimension 1, this one, okay, and also this has dimension 1, okay. So I give dimension 1. As I said, here I can also give dimension 0, dimension 2, and also dimension 2 to this one. Yeah. But this is a dimension 1, but this is another choice. You can also make this choice, okay. But then there is another quantum number that you can assign, which is just the Gauss number, the Gauss number, okay. And here, okay, so this has Gauss number 0. This you usually assign Gauss number +1. This has Gauss number -1, and this is Gauss number 0. Okay. And you see that the BRST symmetry respects exactly this one. So you see it maps something which has Gauss number 0 to something which has Gauss number 1. So in total, this derivation has Gauss number +1. So this is 0, and this is +1. So this is 0, and this is +1. So it's perfectly homogeneous. In this case, for example, this has a +1 and this is +1. So when you do BRST transformation of a Gauss, you get +1 and +1. So it matches, okay? So it's Gauss number 2 from both sides. If you look here, this guy has a Gauss number +1 and this is a Gauss number -1. So then rho has Gauss number 0. And also, of course, this one works easily. Okay. So this assignment of the Gauss charges for the Gauss, for the gauge field, and for the Lagrange multiplier, it is consistent with the BRST transformation. Let me say also S. Now, S in this case has dimension 0, dimension 1, and this has dimension 0, or in this case, but this has Gauss number +1. So the BRST operator has Gauss number +1. Yes. Sorry, the word? Why does the mass dimension of rho? Why doesn't it depend on what gauge fields you choose? Are we going to multiply that by some different function of A to give us a specific gauge field? Right. Depending on what the function of A is, then rho would have a different mass dimension. Yeah, you can actually you can do 2 things. Okay, for the Lagrange multiplier. It depends how you normalize the theory, okay? So in some sense, you can actually change the mass for Lagrange multipliers, okay? It is actually, in this case, actually, it is better to use the first assignment of dimensions in such a way that is homogeneous in dimension. However, you can also have the other dimensions, for example, because actually in front there is the gauge parameter, which in principle you can assign a mass dimension to that parameter, okay? So this is not important. Actually, this is not important when you have, let's say, massless fields. But you have a massless and massive field, then you have to be a little bit careful. Okay, now let's compute this expression now. So if I compute this expression, I get that the gauge fixed action is equal to the invariant one, okay, plus, now here I have to do two terms. One term is coming from just the BRST variation of C bar, so I get a rho of d mu a mu, trace. Okay, and then the terms is coming when x acts on A. So I have to go through C bar. So I get a minus trace of C bar d mu and covariant derivative of C. Okay, so we have these two terms. Okay. Now, first of all, actually, we can check that at a linearized level. So let's first look at this action at a quadratic level. At quadratic level, we have the terms, the usual terms, 1/2 of trace, and then here there is the terms d mu a nu minus d nu a mu squared. These terms is just the gauge fixing, so it is again a trace of rho d a. From these terms, we get something like a trace, just only the quadratic part, C bar d mu C. And then there are interactions. Okay? So you see that also in an abelian case, the quadratic part of the action has the correct form. Nay, first of all, it is gauge fixed, so this is not gauge invariant any longer. If you calculate the equation motion for rho, you just impose that dA is equal to 0. So the dA part coming from this Maxwell action drops out, and then you end up exactly with the action I showed last time, namely A mu box A mu for the gauge part, plus a terms which is a C bar box of C. And this is exactly what you need. But of course here there are now interactions. What I did last time for the Maxwell was completely free, and then we end up with the result. But here we have also interactions. Okay, and then I'm going to discuss a little bit more about this. Why? Yeah, I got these terms because when I perform the BRST transformation, I have two terms. One term give you rho of dA, but then I have to calculate S acting on A. So when I go through, I get minus sign C bar, and then I take the BRST variation of A. So the BRST variation of A gives me these terms. Okay. Good. So this is the situation now. Okay. Of course, you can also change the gauge fixing a little bit. Let me do it now immediately. So if you want to change the gauge fixing and just add the gauge parameter, for example, you can add these terms. Okay. Now, if you do the calculation, so there is an additional terms which is just so there is an additional terms coming by making variation of this one. So you get the plus trace of what is, oh sorry, there's a factor half here, get the factor half xi rho squared. Okay, now you see this is displays the role of the gauge parameters. So now if you calculate the equation of motion for rho, if you calculate the equation of motion for rho, you can actually substitute in place of rho exactly minus the derivative of A, and you end up with the usual Feynman gauge. So this is the usual Feynman gauge. Let's say this is a Feynman gauge when xi is equal to 1, otherwise this is usually called arc C gauge for xi different from 1. Okay. The xi is equal to 1 is called Feynman gauge. If you take the xi is equal to 0, it's called Landau gauge. Landau gauge. Okay. So now let's analyze a little bit this model. Let me write down. So S of C is equal to minus half of CC. S of C bar is equal to rho. S of rho is equal to 0. Okay, let's analyze a little bit this action here. Okay, so we know that this action. Okay, so if you look at it, so there is a quadratic part. Okay, and the quadratic part allows you to construct two propagators. The propagators for the gauge fields, which are usually design in this, draw in this way, nu and b, and of course it depends on this gauge choice. Okay, it depends on the gauge choice, and of course there is. Okay, so let me write down in this way, and of course there is the propagator for C bar C. Okay, and the C bar C usually it is represented in this way, but of course since there are two fields which are different, this is C and C bar. Okay, then you have you have also a direction on this line. It is like a fermionic direction where you have a direction, namely going from C to C bar or to C bar to C. Okay. Now you see the full Lagrangian, it has a Gauss number 0, okay? So this has Gauss number 0 because the gauge field has Gauss number 0. This has Gauss number 0 because rho has Gauss number 0 and A is Gauss number 0. But this has Gauss number 0 because C has Gauss number 1 and C bar has Gauss number -1. So the total action has Gauss number 0. But of course, this is not the full set of Feynman rules that you add. You have the other 3 Feynman rules that you have to add to the theory. One Feynman rules is coming from the interaction terms for the gauge fields. And so we know there are 2 interaction terms. There is a triple vertex like this, okay, which it contains a derivative here, okay, and then there is a 4-point function or 4-point vertices for the gauge boson in this way. But then you see that here in this expression there is the covariant derivative. So if you expand this covariant derivative using the definition of the covariant derivatives, which this one is just the covariant derivative of the Gauss, okay? So you get an interaction between the Gauss and the gauge field. So namely you have an interaction of this type. This looks like the interaction for a fermion, but instead of having a gamma matrices here, you get just a one derivative. Okay, so there is an interaction. There is a vertex of this type. So this means that when, for example, when you calculate the 2-point functions, so you calculate the 2-point functions, mu AB of P. Okay, so this is the 2-point functions which can be represented in this way. So as a mu B, and then there is a momentum here, P mu entering in this 2-point functions. So here you write down the Fourier transform of the 2-point functions written in terms of defective action, or let's say one particle reducible 2-point functions. Okay. Now if I'm going to write down this as at one loop, it turns out that there are 2 contributions. So at one loop there are 2 contributions. There is this contribution coming from the gauge bosons, okay, but then there is another contribution coming from the Gauss, loop. Okay, so there are these 2 contributions in these expressions, and so therefore you have to take into account the Gauss loop, okay, in such a way that these guys turns out to be still transverse. Of course, if you consider 3-point functions, for example, if you consider 3-point functions, also get some Gauss corrections every time. But also, let me tell you also that also this vertex here, okay, this vertex here, which is just a vertex at 3 level, get corrected, of course. So if you go to one loop, for example, at one loop, we also have to consider, for example, a 3-point functions, which has 1 vector index and 2 Gauss lines here. So this means that, okay, schematically, let's say graphically, this is just 1 gauge boson entering this blob, and 1 Gauss out, 1 Gauss in. Okay, so this is just the graphic representation for all loops calculation of the 3-point functions. Of course, there is a 3-point function with 3 gauge boson, there is a 4-point function for 4 gauge boson, all the other possible. But essentially, at one loop, already you have a correction to these expressions. Okay? For example, the one loop correction, this will be something like, so you have the 2 lines of the Gauss here, and then you have a correction of this type, 1 correction of this, because there is using this vertex, you can have a correction, or you can have a correction of this type, for example, because you can use the triple point here, okay, and so you build your corrections. Then, but there is another issue, which is, okay, so this is well known, okay, so you write down all the Feynman diagrams, you write down your one loop, okay. However, there is one important point that usually you don't find in the books, and which is crucial, which is the following. Look, when you look at the BRST transformations, okay? So you see the BRST transformation, for example, let's look at the BRST transformation of the gauge potentials, okay? This has 2 pieces. One piece which is linear in the Gauss, okay? So the BRST variation of A is linear in the Gauss, the first terms, but then this is non-linear in the gauge field and the Gauss, okay? So this BRST transformation is non-linear because going to CC, okay? And these guys are linear, okay? So when you get some operators in the variation which are non-linear, okay, this object gets corrected, okay? Namely, suppose that I do the following, okay? Suppose that I do the following. I take this object, which is A mu C, or written in component, let me write down this as in component. In component, let's put an index A. That will be something F, B, C, A mu B, C, C. Okay? Okay, this is a composite operator, okay, because it is made of two fields, okay, one gauge field and one Gauss field. Both are quantum fields, okay. So then, suppose that I take this object and I plug it into a diagram, okay. Suppose that I do the following, okay. I put here, inserted here, exactly this object here, this operator here, okay. And then I put some external lines, okay. So I can ask myself, this object, this composite operator, get corrected or not? So it gets some radiative corrections or not, okay? But then you can immediately see that this object could have a correction of this type. Let's see at one loop, okay? So you have these guys, and these guys produce, let me write down the Feynman rules for this, okay? I usually write down in this way. So this means that I insert this operator, and this operator has these Feynman rules. One gauge boson here, and one Gauss in this way, okay? So this is the Feynman rules associated to this operator, okay? And then, of course, you immediately see that these Feynman rules get corrected. Because, for example, you can have a gauge bosons exchanging this way. Or, for example, you can have something like that. For example, you can have something like this. Let me see. So this, then, well, okay, so you get this. Wait, okay, like... Okay, so you have these lines, okay? So this is one loop correction to this operator. You see, the external lines are again a gauge boson and one Gauss. Also here is a gauge boson and one Gauss, external lines, okay? And then you get one loop correction to this operator. And also you get one loop correction to this operator. Now, this one loop correction has the same power from, let's say, from a Feynman rule point of view as these corrections. Exactly this type of corrections at one loop, okay? So this means that those guys are intrinsically divergent. So if you calculate the one loop diagram in 4 dimensions, you find out that these two diagrams are indeed diverges, okay? So these two corrections are not the same correction that you get for this vertex. Because you see, the Feynman rules that you see here, or the Feynman rules that you see in this expression, are different from the Feynman rules that you get from inserting this operator. Okay, so inserting the composite operators in your correlation function, of course, you need either Feynman rules, and therefore you need other renormalizations. So you wonder actually if the renormalization of the model, namely removing divergences and fixing some free parameter of the model, it is complete. Namely, I have to do something more. Indeed, actually, these two one-loop corrections actually somehow tells you that you have to add some renormalization factors in order to cancel these divergences. This is not the only case. There is another source of these problems, which is the following. Suppose now I consider the other composite operator, CC. Okay. Again, I can write down in component, which will be CB, CA, C. B and CC, okay? And then actually, let me write down this in this, okay, let me write down in this way. So you see, there's two lines here. So if this line is the Gauss going outside, here I have two Gauss going outside, this one, and this one. So namely, I'm inserting this composite operator in my Feynman diagrams, okay? But also this one gets radiative correction. For example, it can get this radiative correction, for example, okay? And this is again one loop radiative correction, which is different from one loop radiative correction of this type. Of course, at one loop they will have some poles, let's say one of Rapsion pole, a few dimensional regularizations, but the structure of this correction is different from the structure of these corrections. Okay. So this means that when you like to renormalize this model, okay? So you want to add the regularization, then to remove all divergences. It turns out that you have to take into account the renormalization of these two composite operators. So there are one composite operator here, and there is one composite operator here, and you have to take into account the renormalization of those composite operators together the renormalization of the model, okay? So usually you see in the book, you see the Lagrangian and, I mean, take It's on Zuber or other books, okay, if you that you like, and you find out the structure of the diagram and tell you, look, we have to do renormalization, you have to add some counter terms to the actions, and blah, 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 okay. However, usually they don't explain you that indeed you have to renormalize also the composite operator appearing in the symmetries, okay? Because the BRST symmetry is non-linear symmetry. The gauge symmetry is just a linear symmetry, okay? Because the gauge parameter is just is not a field, it's not a dynamical field, it's just a parameter. But the BRST symmetry, it is non-linear symmetry. So this is non-linear because it contains composite operators. So how can I do that? Okay. So how can I renormalize the model, taking into account the renormalization also of these quantities? The way was invented by Xing-Justin and Itzikson, I guess, and they do the following: they add to the theory exactly this BRST variation. In this way. So they introduce two sources, okay? Let's say if you look at the original paper, the sources was written in a funny way. Now, actually, nowadays, we used to call these sources in this way. The sources for this transformation is called the antifield A star. Okay, so you add to the theory the following: A mu star, okay? Let me put trace A mu star S of A mu. Okay, so namely I introduce, for the moment, this A star is a classical source, it's a classical field. I'm not going to quantize this field, so it's just a classical field which has exactly the same quantum number as the gauge field, namely is a vector, okay, and it carries also an index in the Lie algebra, or let's say this field has a value in the Lie algebra. Okay. And then there is another one which is called C star, okay, coupled to the BRST transformation of C. Okay, so namely I introduced these two objects here. Those are called antifields. Those are called antifields, and they have the same quantum numbers as the corresponding fields. Okay, so this is the antifields for the gauge fields, this is the antifields for the C. Of course you can say, well, why, for example, don't you introduce also the antifields for the non-minimal sector? Of course you can do it, okay? Namely, you can add here something like a trace, then you have the antifields of rho, S of rho, plus the antifields of C bar and S of C bar, okay? If you look at the paper, the original paper about Xing-Justin, BRST, and the other people, they didn't introduce this term actually, because the reason is the following. You see, the BRST transformation of this non-minimal sector are linear, okay, because it maps one fields into one fields, okay. So these transformations are linear transformation. Indeed, you can make it nonlinear. You can add some pieces here in order to make it nonlinear. If you do that, then you need also the antifields for. Okay, let's say from a renormalization point of view, at this level, at this stage, you don't need the non-minimal. You don't need the antifields for also for non-minimal sector. You can add them. Okay, you can add them. Now, for the moment here, okay, then you can ask yourself, look, I add some pieces to the Lagrangian. I add some pieces. Oh, sorry, I don't want to erase this one. I add some pieces to Lagrangian, but then of course, in order to respect what I said before, namely my Lagrangian will be the gauge fixed Lagrangian, will be the gauge invariant one, plus S of something, Okay. Then, okay, in what I do here is the following, actually. I require that these antifields A star and C star, they are invariant under BRST symmetry. Okay. So S of A mu star is equal to 0, and S of C star is equal to 0. Again, I can add also the other one, just require that those are invariant. So all these other fields are put invariant. Please notice the following. That these fields, C star and A star, are classical fields. Okay, so they are not quantum fields. So I'm not going to quantize those fields. Okay. Now, if I do that, if I add this, so you see that this piece of the Lagrangian can also be written as of something, because I can write down these pieces. Okay, so this was the gauge fixing, so C bar, so dA mu plus psi rho. That was the gauge fixing that we had. And then, of course, I can also add here A mu star A mu plus C star C plus rho star rho plus C bar star C bar. With some minus sign. So this has a minus sign here. So this has a minus sign here, this is plus, this is a minus sign here, and this is plus. Let me explain this sign here. Now you see, please notice the following. The variation, the BRST variation of the gauge field A, it is anti-commuting quantity, because A is a commuting fields, S is nanti-commuting derivation, so is nanti-derivation. So therefore, the full combination S of A is anti-commuting. Okay. So therefore, if I want to couple this anti-commuting quantity to the action, the anti-fields which is in front of it, it must be anti-commuting again. Okay, so you see, this is anti-commuting and this is commuting. When I act with S, if S acts on A star, give you 0, but then I have to go through this A star, so I get a minus sign, which changes this minus sign, and I get exactly these expressions. The same thing is happening here, but you see, S of C is an anti-commuting fields, S is an anti-commuting, so S of C, it is bosonic, it is commuting, so therefore C star is commuting, okay, and therefore I get a plus sign here, okay, and again the same game. Rho star is an anti-commuting because rho is commuting, and C star bar is anti-commuting, so is commuting because C bar is anti-commuting. So let me make a table now. Well, I will draw it again, okay. Let me make a table, okay? So we have the following: A, C, C bar, rho, A star, mu, C star, C bar star, and rho star, okay? Now let's say Gauss number, okay? This is 0, plus 1, minus 1, 0. And you see the following, okay, this guy, this combination here has Gauss number plus 1 because it's this BRST acting on the gauge field. You also see from here the BRST variation of the gauge field, it is the covariant derivative of the Gauss, so a Gauss number 1, okay? So this means has Gauss number 1, but the total action must have Gauss number 0. So therefore A star has Gauss number minus 1. So this has Gauss number minus 1. This has Gauss number minus 2, because you see SC produces 2 Gausses. So this actually Gauss number 2. This must have a Gauss number minus 2 in this way. So this guy has Gauss number, S of C bar is rho, which has Gauss number 0. So C bar has Gauss number 0, and this one rho, in principle, this Gauss number 0, S of rho Gauss number 1, this must have Gauss number minus 1. So these are what is the Gauss number, okay? Actually, you can add another number, which is called antifield number. Antifield number, okay? And the fields have antifield number 0, and then you assign antifield number 1 to the antifields in this way. What about the statistics? So this is a boson, okay? This is a boson. So this is a fermion, this is a fermion, this is a boson. Now this one is a fermion, this is a boson, this is a boson, and then this is a fermion, okay? So the statistics of the antifields is exactly the opposite of the fields, okay? To be very precise, if this one is a gauge fields, okay, so to be very precise, if this guy is a gauge field, let me write down in this way, okay, so as an index mu down, because this object is a part of a one form, okay, so it is the component of a connection which is one form, okay, with the Lie algebra value, so it is a vector in the Lie algebra, okay. The antifields A star actually has exactly the opposite quantum number, namely this guy is a part of a vector, okay, is not of the one form, okay, and the index is A is down, which means is in the dual of the Lie algebra, okay, in such a way that this contraction, let's say this expression here, or if you like this expression here, okay, actually the contraction is not just made with the scalar product, but is really the fields and its dual fields, namely these are index and this has the dual indices, okay. So there is essentially here in this expression there are no metric involved, neither in the Lie algebra nor in the gauge, let's say in the vector indices. The same things happen for C star, has exactly the opposite indices of C, and so on and so forth. Yeah, yeah. No. A classical field because they are not dynamical, so they do not propagate. I'm not going to write down a propagator for those fields. So they do not. When you write down the path integral, you don't integrate over them. Okay. So they are classical sources, really classical sources, but they have a statistical property, namely the A star is an anti-commuting fields and C star is a commuting. Okay, but they are sources. Okay, external sources at the moment. Okay. Yeah, sure. It's just because actually what I want to do, I want to add something to the action which is BRST exact. Okay. But first, the second things, I want to couple the sources to exactly to the BRST variation. I will show you why I'm doing that. Okay. There was another question. Yes. Yeah, no, exactly, no. This antifield number is not a symmetry, right? Okay, it just counts the antifield number here. Okay. For example, let me tell you why you introduce this antifield number. For example, if you see the set of Young means, you consider, for example, gravity or supergravity, for example. In this case, actually, the symmetry, it doesn't really close on structure constant, but it closes on structure functions, which contains also the fields in it. So there and up to also to equation of motions, okay? So then the action will not be linear in the antifield, but will be non-linear antifield. So you get first order antifields, second order antifields, and so on and so on. These antifield numbers allows you to take into account what is the expansion on the antifields. It's not a symmetry for that, yeah. There is a way to combine the antifield number and the Gauss number in order to make it kind of auxiliary symmetry, okay, in some cases, yeah. Okay, so why I do that? Well, I do that exactly because now actually I have exactly the sources, okay, and when I'm going to renormalize the model, I'm going to renormalize the model, but using these sources too. Namely, what I'm going to do is renormalize the model, but with all the sources written like this. Okay. So therefore, the renormalization take into account also the renormalization of these composite operators. So this was the reason why these antifields were introduced at the beginning. Okay. Yes. Exactly. Good. This is the good point. Namely, at this level is just the classical BRST symmetry. Now I have I want to go beyond the classical BRST symmetry. Okay? To go beyond one loop, or let's say to do the perturbative expansion, I need to derive word identities. Okay, so now I want to derive word identity. Actually, there are 3 word identities here in this game. Okay, the first word identity is just to tell the theory, or let's say to say which kind of identities must the Green's function satisfy. Okay, so there are 3 identities, 3 equations. Okay, the first equation is the following. Look, I add the gauge fixing, okay, but this is a choice, okay, it's my choice, all right? So therefore, I need to implement at the quantum level this choice, okay? So of course, what I'm doing is I'm writing down Lagrangian, but the Lagrangian, let's say my teacher, actually my professor, was used to say, okay, the Lagrangian is just an opinion, okay, but what actually is important are Green's functions, okay. So every information, exactly to do the extension to perturbative level, every information should be translated into Green's function or into word identity among these Green's functions. So the first ingredient is the gauge fixing. Now you see, if you do all this game, and then you let's take the variation of the gauge of the effective action with respect to the gauge to rho, okay, and then this is equal to what? Is just d mu a mu plus xi rho. Okay, this is just the equation of motion for the rho Lagrangian multiplier. Okay, gamma. Okay, gamma you can read it in this way. So gamma at the 3 level, just coincide with the action S, so which is just the integral of my gauge fixed Lagrangian. That's at the 3 level, okay? But then if you go beyond the 3 level, this guy contains all the loop expansion. It contains one particle irreducible one loop expressions, okay? For example, the bubble, all the possible Green's function, you get it by taking derivative with respect to the fields. So actually, this is a functional, is actually, most precise, this is a generating function for one particle irreducible diagrams, okay? Of course, this equation is satisfied at the 3 level, namely at the 3 level tells you that the variation of the action with respect to this parameter is this one. Now I'm going to do the following. I'm promote, okay, this equation to all loops, okay? So for me, that will be a word identity, or let's say it's just a condition to my effective action. Can I do that? Well, you see, this, of course, this is a very complicated expression because this is just an equations for this big object, which is generating function or one particle reducible, which is very complicated quantities, very complicated object. But then we know that the variation with respect to rho, it is equal to these 2 fields, derivative of A and psi of rho. But you see, in this left-hand side appear only linear operators, because this is linear, d mu and mu is a linear operator, and rho is just a field, so again is linear operator, okay. This is, let's say, the easiest solution. Of course, you can add the gauge fixing, which is much more complicated. For example, suppose that I want to choose another gauge fixing. Instead of this one, I want to add something like a squared, for example, or I want to add something rho squared, okay, or something like that. Suppose I add some nonlinear terms to my gauge fixing. It turns out that this equation gets the nonlinear terms. If you get nonlinear terms here, you need to add auxiliary sources in order to take in renormalization also nonlinear operator here. I'm going to do the easiest things, namely I do just a linear gauge fixing. Okay, and already there it's already a mess, but so this is the first equation. What about the other equations? Yes? Yes. Yes, it does. Right. Exactly. So you start with a particular gauge and then you get normalized, okay? So this equation control partially this property, okay? To take into account the renormalization of the gauge parameter, you can do something which is the following. You can extend the BRST symmetry also to the gauge parameter. You say the gauge parameter transform into some constant Gauss, okay? If you do that, you can write down another word identity which control exactly how the gauge parameter it is renormalized, okay? So actually, when you invented this BRST symmetry, then you can play with this by extending it in several ways. For example, last week Nathan Berkowitz was discussing, for example, zero modes. Okay, for example, zero modes, and then you want to write down your you was write down some correlation function and has to take into account some zero mode. And actually you can perform a BRST variation of this zero mode, adding like a supermodulize to the Riemann surface, and to take into account how these actually are correctly renormalized in this model. So you can extend it in this way. Good. So the second equation I'm going to discuss is the following. Now I want to write down the word identities for the BRST symmetry. Okay. Now, to write down the word identity for the BRST symmetry, I observe the following. If I make do you remember that if I make a variation of gamma, the variation of gamma is the following. I will do it by chain rules. Okay. So it's this variation of A mu, d of d gamma of A mu. Then I have S of C, d of gamma C, plus S of C bar, d gamma respect to C bar, and then finally S of rho, d gamma of rho. Okay? I just calculated what is the BRST variation of this functional. Okay? And then you see the following, okay, that here it appears the variation of a mu, this variation of the Gauss, variation of the anti-Gauss, a variation of rho. Okay. Now let me use the BRST symmetry. Yeah? No, for the moment let's forget about that. Okay, it's not for this particular setup is not useful. So it's just only a decoration in this moment. Okay. Let me now do the following. You see here it appears exactly the BRST variation of the gauge field. Okay, but I exactly erase it. What I want to say. Okay, so there was like a rho dA plus. Okay, so this is my Lagrangian. Okay, so you see that the variation of the gauge field here actually can be viewed in this way. This is nothing that the variation of my action with respect to the sources, to the antifields. Okay, you see, if I take first a moment, let's take instead of the full generating function, let's take the action S, which is just a tree level of this. Okay, then you see that the variation of the action is given by this expression. Of course, it is equal to 0. Okay, but then here I do the following. Every time I find the variation of the gauge field, I substitute the variation of the action with respect to the antifields. Now here as a C, this is what is the variation of C star. Okay, and this is S of C bar. Now S of C bar is rho, is linear. I don't have any problem, put a rho here. And S of rho is equal to 0. So S of S is equal to 0. This corresponds to the following. D square X. So first I will write down for S. S respect to A star mu A, variation of S respect to A mu, plus variation of S respect to C star ds of C, plus rho of ds of C bar is equal to 0. Now you can check it by yourself. I will advise you to do that, namely to take this action, okay, and to compute this variation, okay, and do the calculation and find out that this object is equal to 0. Okay, you can check it by yourself. And then I replace instead of S, I replace S with gamma, and then I find out this equation: d for x, d gamma of A star mu A, d of gamma of A mu A, plus d gamma of C star d gamma of C, plus rho d gamma of C bar is equal to 0. Okay, so this in the literature is known as the Slavnov-Taylor identities. Slavnov-Taylor identities. This expression here, okay? Sometimes is written in this way, okay? So this is what is known as Slavnov-Taylor identities. Please notice the following, that these identities here, okay, compared to the word identity that we wrote on Monday, actually, you see, this guy, it's very complicated now, because it becomes a non-linear partial differential equation. Well, essentially is a functional partial differential equation for gammas. But you see that it becomes a very non-trivial equation because it becomes non-linear. The word identity for the gauge symmetry were linear equation for gammas, okay? Because the gauge symmetry was just a linear transformation. But the BRST symmetry is non-linear transformation, and you end up with very complicated expression like this. Right. This expression here, it is just at the level of the generating functional, the expression of the fact that your action it is BRST invariant. All right. But this equation now actually I translate this equation for all Green's functions. So all Green's functions must satisfy these equations. Okay. Right, exactly. So we have to enforce this equation order by order. So this means that when you expand this equation order by order, for example, if you expand this equation at the first order, okay, so this means that this has a 0, 3 level, and this is one loop, or you get one loop and 3 level, and so on. But when you go to 2 loops, for example, you get 2 loop, 3 level, but you get also 1 loop and 1 loop. Okay. So this is exactly what I asked your colleague. Namely, the BRST symmetry get renormalized because of this. Namely, this conspire to give a renormalization of the, let's say, of the Lagrangian, but also the renormalization of the symmetry, because the symmetry get renormalized order by order. Is exactly the fact that you have non-linear terms of this type that you get contribution to all orders coming also from low order contributions. Okay, this is So this is in fact a very deep equations, because now it takes on to go to the n loops. You need to renormalize all the loops behind that. Otherwise, you don't get the correct symmetry at the quantum level. So this equation contains the renormalization of the model. Okay, if you impose this for the model, but also the renormalization of the symmetries. Okay. Now, of course, imagine that if you consider, for example, supersymmetric models, for example. If you consider supersymmetric models, it turns out the following, okay? So certainly you have the gauge symmetry. Suppose you consider super Yamis. Professor Terashima was discussing super Yamis, and super Yamis has, of course, gauge symmetry, okay? But also you have a supersymmetry, okay? So, and then the supersymmetry was also quite complicated symmetry, because it contains equation of motion. It contains also, I mean, it is close up to equation of motion, up to gauge symmetry. So therefore, one way to do it, for example, is to promote the BRST symmetry also to contain the supersymmetry. So you can extend the BRST symmetry to contain gauge symmetry, BRST supersymmetry, conformal symmetry. So you can extend. So every symmetry that you have in your theory, it could be linear or non-linear, you can promote to BRST symmetry. And then you have one big equations, this equation which is called Slavnov-Taylor equation, and now in the modern literature it is known more like a master equations, okay? So I will tell you what is the master equation, which is just a simplified form of these equations, okay? But that's actually, that would be the key for understanding the theory at the quantum level, okay? At the quantum level, both from a normalization point of view, but also from a classical point of view. I told you that there are 3 equations, okay? The 2 of them is just the gauge fixing and the Slavnov identities, okay? There is a third one, okay? And the third one, you get it by computing the commutator between this operator here and this equation here. Well, how I can do that? Well, you see, this quantity here, it is S of gamma, it gives you this one, okay? You can construct an operator S, okay, which is just the linearized version of this. Namely, you take an operator which has the following form. S, let me write down in this way, S, which is an operator with the following form. D gamma of dA star of D of dA plus D gamma of dA, D of A star, and so on. Namely, I just expand the first order, essentially, this equation. So I can write down differential operator in such a way that when S acting on gamma, S acting on gamma, this reproduces these equations, okay? Equation for gamma gamma. Okay. So then, so this is a differential operator, okay? There is one small detail that you have to take into account. Indeed, you see, if I write down in this way, when act on gamma, I have two pieces. One gamma appear here, one gamma appear here, and so I'm duplicating these terms, okay? So in order to be correct, actually here there is a factor half in front. There is a factor half in front on nonlinear terms, and there is no factor half in front of nonlinear, or the linear one, okay? Rho d of C star. Now this is, you see, this is a linear differential operators. Well, functional differential operators, which is linear in this derivative, in these functional derivatives, and it contains this gamma here. So S of gamma reproduce exactly my Slavnov-Taylor identities, okay? But then I can calculate something of this type. I can do the following. So if I calculated the commutator between these differential operators and these differential operators, okay, this again is the differential operator, it's just a derivative. If I calculated the commutator between two, okay, I get one additional equations, okay. One additional equation, which is the following, okay. You can check by yourself that the consistency between this differential operator and these differential operators here, okay, a consistency give you an additional equations, which is the following, okay. Let me see. Yeah. Right. D gamma of C bar plus D mu of D gamma of A mu star, A is equal to 0. Okay, so this is another equations, which is again linear, okay? So you get one equations, two equations, let me say, two equations, and the third equation is this one. Okay, so you have a three functional equation. This equation is called Gauss equation. Gauss equation. You see that here also appear the antifields. So you can check, for example, this three system of equation, namely the Slavnov-Taylor identities, the Gauss equation, and the gauge-fixing equation, forms a closed systems. Okay, namely it gives you an algebra of differential operators where it closes. Okay. Now there is a theorems that's called Frobenius Theorems, which allows you to tell you that if the algebra is involutive, then you can solve this algebra. Okay. So you can construct a solution of this algebra. So then now you do reverse engineering. Okay. You say, well, forget about the action. Okay. I forget completely about the action, okay? I keep as my ingredient what I wrote on the blackboard, okay? So this is my theory, okay? So Yang-Mills, quantum Yang-Mills, okay, in 4 dimensions is completely described by these ingredients, okay? Namely, those are the fields that I have in the game with this assignment. Okay, with the quantum number assignment, all right, okay. So, and then I choose gauge fixing, and the gauge fixing is written here, okay. The symmetry is written here. This is the complete symmetry of my theory. Okay, the BRST symmetry is completely written here. Consistency between them is just the equation of Gauss. Okay, and then the last bit I need is that the tree level coincide with the action. All right. Okay. Then you can say, then you can ask yourself, can I take these three equations, okay, and then I can calculate the solution of these three equations, okay? So one can try to solve these three equations, okay, namely to write down with this gamma, okay, which solve this equation. Of course, that will be very complicated because you need to go higher with the fields. But let's consider only the first terms, namely the action. Okay. Then you can ask yourself if you take only the tree-level contribution. Tree-level contribution means that you stop the calculation of operator at the dimension 4, okay? Because these are the maximum type of operator that you have in the actions, okay? So you stop at dimension 4, and you ask yourself, this equation at the dimension 4 reproduce completely the action? The answer is yes. Namely, the action given by the solution of this equation coincide exactly with the action that I wrote before, okay? So this means that these three symmetries, okay, I'm going to answer. These three symmetries plus these quantum numbers, and with the fact that the tree level coincide with the action, reproduce exactly my action. So that will be my starting point, okay? Not the action. As I said before, action is an opinion, okay? I want to encode my opinion, so my knowledge about the action in these symmetries plus quantum numbers, and trying to recover the action out of these symmetries. What was the question? Okay. Okay. 5 minutes break. Okay, thank you. Huh? This one, you have to take into account the consistency between these equations and these equations. Okay. You can do the commutator between the differential operators. Okay, you know the Frobenius Theorems. Frobenius Theorems that tells you that if you have one vector field and another vector fields, and then you calculate the Lie bracket among these vector fields, it could happen two things. Either you have a new vector fields, okay, and then you have to add to the algebra, okay, or is the one of the original vector fields, okay. Once we have completed the algebra, then by Frobenius Theorems tells you that there is a solution of this algebra. Okay, so this is status now. So we have this is a set of equations. We have a set of quantum numbers, and then actually I'm not going to solve it, okay? But I want to do it first. I want to simplify a little bit these equations, okay? In such a way that I'm directly going to this Batali-Vilkovsky framework or master equations. So then I rephrase it in a more mathematical way, okay? So I want to solve it a little bit, this system, or to simplify. So first of all, I do the following, okay? I do a very simple things. I say, let's define a new gamma. Okay, let me call it gamma hat, which is gamma minus this expression, so dA plus xi over 2 rho times rho. Okay, so namely I remove from gamma just the gauge fixing. Okay, so of course the theory is quantum theory. I have a gauge fixing and everything. I just redefine gamma in such a way to remove this expression. Okay, so this gamma hat now satisfies simplified equations. A simplified equation. You see, because the gamma hat now gets simplified, and you see that the equation for gamma hat becomes now gamma hat of rho is equal to 0. Okay, so the first equation tells me that this functional new function gamma, it doesn't depend on rho. Fine. The second thing is that I'm going to solve this equation. So this is a linear partial differential equations, okay? And that is very easy to solve it. And to solve it, you just redefine these fields, these anti-fields, in this way: A mu star A minus derivative of C bar. I redefine in this way, okay? And right? I redefine in this way, okay? In such a way, when I'm going to rewrite gamma hat as a function of gamma as a function of A, C, C bar, no, not C bar, wait, yes, C bar, sorry, A star hat, C star, in this way. Rho is gone because this doesn't depend on rho, okay? Now I redefine A, okay? If I redefine A, it turns out the following. The D of gamma hat is independent of C bar, okay? So this new object doesn't depend on C bar, okay? And then finally, I can rewrite my Slavnov-Taylor identity in a simplified form. Yeah, so if you do that, okay, if you redefine in this way, this you get simplified this equation, and then you get the d gamma hat is equal, right. So finally, my Slavnov-Taylor equation written in terms of this gamma hat becomes a very simple one. But well, simple, okay, rather simple. Is equal to 0. Okay. Somehow I get rid of the linear part, all this other information, I get rid of it, okay, and I end up with this expression, okay. And now where gamma hat is a function, is a functional of A, C, A star hat, and C, and what? And C star. Right. This is differentiated with respect to a hat. Yes. Yeah, sorry, here. Okay. Okay, so now we end up with these interesting equations. Okay, this equation has been studied in several ways, and this is now in the literature is also called master equation. Master equations. Okay, let's forget where it comes from. This derivation, you find it, I think you find it in the Zixon-Zuber, or you find in these notes, in this reference I gave you. Okay. Now let me try to do the following. Okay, first of all, I will try to rewrite these equations, okay, in the following way. First of all, I introduce a bracket, which is known as anti-bracket. The anti-bracket is the following. Okay, so if I have two functional f and g, okay, then the bracket f comma g is equal to integral d for x. Then you have a df respect to a star dg respect to a plus df respect to a dg respect to a let me write down this g f a star a plus again df of c star dg of c plus df dg of c star and df of c. Okay. Now here I suppress the indices. Every time you put by yourself the indices. In this way, of course. Right. So this bracket here has several interesting properties. Okay. Of course, this bracket here, okay, it reduced. If I plug here gamma hat, this reduced to the Slavnov-Taylor equations. But this bracket here has a nice properties. Has a nice property which is the following: if you calculate the bracket fg with the third h, this gives you 0. Namely, acting twice with this bracket here, it gives you 0. Okay, this follows from, because you see these guys as is a commuting quantity, this is anti-commuting quantity. So in each terms of this Lyapunov identity or the master equation, there is one bosonic things and one fermionic fields. Okay, then you just apply this twice, and then you find out that actually it vanishes. So it gives you 0. First, the second thing is now, what happens, for example, if I do the following? So suppose that now let's take of course this equation here is satisfied by my action. Okay, the action S, the original action S, built out of my gauge fixing invariant Lagrangian, it's satisfied automatically these equations. Namely, if I calculate the S with S, that is 0. So this is called classical master equation. Classical master equations, okay. And of course, at the quantum level, this is satisfied by gamma. This is the quantum master equation. Okay. In principle, what usually is called quantum master equations has an additional piece on this side. Okay, you find in some books something like H box of S, this delta of S of gamma. Sorry. For example, if you want to see this, there is a nice reference. There is a book by No. Teitelbaum. The title of the book is Quantization of Constraint Systems. Okay, there is a nice book, and actually they discuss the classical action, classical master equations, the quantum action, but also this deformation here. At the moment, actually, I mean, the deformation, namely this, instead of being 0, is something of these terms with h bar, so this means it's a quantum corrections, okay? It's somehow derived in the formalism. Namely, if you have the master equations, the quantum master equation of this form with these corrections, it seems to be consistent with the rest of the theory, but at the moment, nobody was able to build a theory which actually has a consistent deformation of this type. Okay, so there is only one example, which is like constraint field theory, which produces something like that, but this doesn't seem very consistent anyway. So it's okay. So therefore, I'm not going to discuss these deformations. Okay, so the quantum master equation is this guys. Yeah. Yeah, not really. Okay, there are some conditions on this. Okay, in such a way that this guy is not an anomaly. Okay, but is consistent. So I will come to the anomaly in the last lectures. In the last lecture, I will tell you how the anomaly are somehow. After Luca Griguolo has discussed anomalies, I will show how the anomaly enter in this game. Okay. Yep. Here. Yes. Oh yes. This means that if you replace instead of f and g are two generic functional. Okay. Instead of f and g, you take gamma. Okay. Then it gives you the Lyapunov identity, and this is equal to 0. Okay. Now, actually, what you can do the following. You can define, a differential operators, which I'm now going to call it s, small s, okay, to be different from the s that I was using before, the calligraphic s. I use a small s, okay, and I define this s in this way. I take the bracket with s with any fields. Okay, so namely, if I do s of a mu, a, this is just my action s times A mu A. Okay? So this is just definitions. Okay? Using this property here, okay, you can check immediately that this definition tells you that S square is equal to 0. Okay. But let's now do the calculations, okay? This is very interesting. Let's do the calculation. So I want to calculate what is S acting on these fields, A mu A star, hat, C star, and C. Okay? I want to calculate what is this operation here acting on these fields. Okay? So this means, let's start with S, acting on A mu A, which means S with A mu A. Now, if I plug in this master equations, okay, let me write down for you the master equation here. Okay, what is S? Now S, it is just the gauge invariant part plus the BRST Then what is S, S? This is just D for X. This is hat. Yeah, okay. Okay, so those are the ingredients, okay? This one. This is just the coupling of the C star, which is the antifields, to the BRST variation of. So that actually this was small s. Okay, okay, yeah. Sorry. Okay. Yes. Yes. Big S is just the action here. This is big S, which is the original actions, okay? The original actions after I remove the gauge fixing and everything, okay? Right, the small operation S, okay? We forgot that. Now you define a new one, okay? A new one, I will show you the relation between the new one with the old one, okay? If you do the calculation, this is well, you do it because S acting on A gives you just a variation of S with respect to A mu star A, and this is equal to what? To little s of A mu A. Okay, so the small new s correspond to calligraphic S on the gauge field. But now let's see what happened on the antifields. This is very interesting. So it's S acting A mu star. Now there are two pieces. Okay, so let's do the calculation. This is just D for X. Now I have a variation of the action with respect to the A mu A, and then here I have the variation of S with respect to A mu star. Okay, this is in the identities, but instead of one S is this one, and then here I have to put A star, and then of course there are the other way around, D of A mu A hat. Let me use different indices, otherwise you get confused. So it's new B. This is new B D of A new B star acting on S. So let me do it slowly. Okay, so the bracket is f and g is the following: d for x, df of a star mu a dg of a mu a plus d of g dA mu star a df of a mu a plus df of c star dg of c a plus dg of c star a df of ca. Okay, so this is just the definition of the bracket. Okay, so when instead of f and g I put ss, I get this expression, which is equal to 0. Okay, now here I put one s and one field. Okay, so if I do that, so s is this one, so instead of f I put s, and instead of g I put a. Okay, now of course if g is a, I get only contribution from this term. This is 0 because is g respect to a star is 0. This is g respect to c is 0, and g respect to c star is 0. Okay, so the only contribution that I get from this expression is s acting on a is just derivative of s respect to a. If you do the calculation, of course, when I say that this is just 1, is this g respect to a mu a? Suppose that the g is now a field, okay? This actually gives you, suppose that this is just a field, exactly this field, mu b. Of course, this depends on x, this depends on y. If I calculate this functional derivative, this gives me the following: delta mu nu, delta ab, and the delta of x minus y. This is the functional derivatives. Okay, so there are 4. When I integrate over the axis, okay, I end up with something which is local in the things. The same things happen for the indices. The index mu is contracted, the index a is contracted here. So here I get the delta functions, and then I get these expressions. Yes, on purpose, yes. Because essentially the antifields must have exactly the opposite indices.
It's opposite of how we define it, so we have a mu.
Okay, so essentially, yes, okay. In this way. To be precise, okay, because this was a connection, yes, it's one form, yes. Okay. Right, and these are hats. Yeah. Yeah, essentially after you define it, you forget the hats. Okay. Okay, now let's do the calculation for S on A star. Okay, S on A star. So S on A star, of course, again, if G is A star, of course, this gives no contribution. This gives you 1 contributions, okay, and so on. So, but then you find out that this guy is what? Is the variation of S with respect to the gauge field, A mu A. Okay, but then you see the following: that this guy has 2 contributions. Okay, the first contribution is coming from the invariant part. Okay, so there you get something like a minus d mu f, covariant derivative f mu nu of A. And then there is a part coming from here, and this part coming from here has the following form: A, so it is just A nu star times C with index A. Yeah, if you do the calculation, I think that there is IG in front here. Okay, so you see that the BRST, let's say this S variation of A star contain 2 interesting parts. There's this part here, which is just the equation of motions of the gauge field. Okay, and there's another part which is these guys. Okay, and then you see that this seems that the A transform in the adjoint representation. Okay, not as a connection, but as a like in the adjoint representation of the Lie algebra. Okay, let's go on. Okay, let's compute what is S of C A. This means S on C A. If you do the calculation, this is just the S of C star of A, and this gives you minus. Well, it gives you what? It gives you just S of C A. And finally, okay, you can calculate it with this S of C star A. Okay, again, you do the calculation. You find out that this is the variation of S with respect to CA. I will going to write down in a better place here. Okay, so S of C star of A, which is just S acting on C star of A. That gives you the variation of the action with respect to CA, which is just, you pick up two pieces. One piece is coming from here, which is just the covariant derivative of A mu star A, and there is another piece coming from here, which is a plus IG of C star C A. Okay? So now what happens the following? It happens the following. You see that this variation, S variation of A, gives you just the BRST symmetry. Okay? And in fact, the S variation of C gives you just the BRST symmetry. Okay? But the S variation of the antifields, namely this one and this one, okay, gives you something more. It gives you the equation of motion of the original fields, okay, plus something, which is this one. Okay? You see this one and this one. Okay? Okay, the way how this is constructed is the following. This operation S, okay, it can be decomposed in two operations. Okay? The first operation usually is called gamma, and the second operation is called delta. Okay? This operation gamma here, okay, it is now renamed, okay, as the BRST symmetry. Okay. In fact, this gamma here coincide with on the fields with the BRST symmetry of the fields. Okay. But in the gamma, actually in the gamma, there is something more. Okay, something more, which is just the transformations of the antifields. So this part here and this part here are inside of the gamma. Okay. This operator here is called Koszul Tate operator. Koszul-Tate operator, and implements the equation of motions. The equation of motion. In fact, in this case, the only contribution is coming from this. Okay. So what actually you can check is that now gamma square is nilpotent. You can check that the delta square is nilpotent. And you can check that the gamma and delta anti-commute. Okay? So, okay, so we end up with very interesting structures now, okay, because actually the BRST symmetry, okay, it is somehow enlarged, okay, to consider the BRST symmetry also on the antifields, and the BRST symmetry of the antifields contain these pieces, which tells you that this Gauss C star is in a joint representation of the same Lie algebra, okay, and also, for example, in this case, you see the BRST symmetry is the gamma part. This is the gamma part, okay, and this is just the delta part, okay. So the gamma part of A star is just again a gauge symmetry. It's just a simple gauge. So the rigid symmetry in the joint representation of the Lie algebra, okay. But the delta part actually contains other information, which is the equation of motion. So let's say in the Slavnov-Taylor identity, or let's say in the master equation, it contains not only the symmetry, but it contains also the equation of motion of the theory. Okay, so it has the full knowledge of the gauge symmetry and the equation of motion. So this is the reason why last week actually Nathan Berkowitz was discussing, for example, the cohomology of the BRST operators for superstrings, and at some point he was showing that also emerging the equation of motion for the vertex operator, which translates into equation of motions of let's say of the gauge field representing such a vertex operators. Okay, that's the interplay between the equation of motions and the symmetry is realized in this way using these master equations. It's actually beautiful because this let's say this framework, this structure here, it emerges completely in the string field theory. For example, if you do it in string field theory, what it emerges exactly all this structure just from the structure of the theory for the string field theory. Namely, you get all this symmetry and the equation of motion completely automatically implemented in the string field theory framework. If you want to, let's say, if you want to read it, you can look in the first reference I gave you. Okay, in the first reference I gave you, there are this construction for Yang-Mills, Chen-Simon, superparticle, not superparticle, but particle, and then in the report, in the physics report, you find out also the application to string field theory. It's very beautiful because in the report is done step by step. Okay, namely, in the first section it discusses the gauge invariant formulation. Then it did the gauge fixing. Then he did the BV formalism, and then every time he replaced. They do the same exercise, the same examples in all these fashions, in all this framework. It's actually it's very nice paper. Okay. All right. So. Okay. So once actually. You've done this one, okay. So then you can easily actually update to adding more fields. For example, if you want to add the matter fields, for example, if you want to add other gauge fields, or if you want to add other structures, okay. The structure will be always the same, and you can build these master equations. Now the point is to solve this equation, namely, and to check actually if you can find an action, okay, you find an action which satisfies such an equation. I will suggest you to check, for example, that these guys given like this, okay, satisfy exactly these equations. You can check it by yourself, but it's interesting because at some point you get the equation of motion for Yang-Mills here, and you have to play a little bit with the partial integrations, okay, to see did they indeed satisfy such an equation. And then when you know that the classical action satisfies this equation, then you can trust this equation at the quantum level, and then you perform this analysis at the quantum level. So those questions, yeah. How? Yeah, I could imagine that I put in gamma my. Okay. One way to do it. Okay, one way to do is the following. Okay, is now assign some quantum numbers. Okay. So these guys actually it raises the antifield number. Okay, and this one it doesn't change the antifield number. Okay, so there is a natural gradation, natural gradings among these operators, and then using these gradings you can do these differences. But actually, it depends. You can change this grading in some sense. So you can shift part of the pieces one to the other. It depends what you want to do. Okay. Now this framework actually works not even for Lie algebra, but even for more complicated theories like for supergravity. Okay. Yes? Yes, right. Right. Yes. Yeah. Let me. Okay. The interplay between these two frameworks, it is done in this way. It is done in this way. Suppose that I consider an object which is a string field, okay? This object, a string field, is, okay, I take it very easy, which is the following. I just take some fields, okay, which depend on space-time, or the target space, okay, acting on some states on the Hilbert space, on my worksheet, okay? So these are the states on the worksheet, name of the Hilbert space of strings, for example, okay, that Nathan was discussed last time. And these guys are the target space of the thing, okay. Then there is the following equations, okay. So the Q on the worksheet, the BRST on the worksheet, acting on psi, is equal to the S, this small s, acting on the psi. Okay, so there is this interplay. This Q is acting on these guys, on the states on the Hilbert space. Okay, so this Q was Berkowitz was discussing last week, acting on these states. Okay, and then you can use, of course, X also it could be part of the states because it's also quantized. Okay, and then actually you can phrase this equation. Now this S is the operator that I discussed here at from quantum field theory point of view, acting on these states. Okay, so this is the interplay between the BRST on the worksheet and the BRST in the target space. Okay, this equation actually is the equation that you get from string field theory. Now, the BRST on the worksheet, it is translated into the BRST, or let's say better, into the master equation in the target space. That is the interplay between the two. Okay, it's beautiful. It's really beautiful because in string field theory it happens the following: that it doesn't give you the BRST, but gives you really the master equation, which contains fields and anti-fields. So this is the reason why last week Nathan was discussing also the fields and anti-fields emerging from his framework, because the fields and anti-fields from first quantized point of view actually now are interpreted, are understood from this Battle-Wilkowski framework, or this fields and anti-field formalism. Okay, so this actually, this equation, I think this equation was due to Ashok-Sen. Okay, Ashok-Sen actually, where I was able to prove the relation between the BRST charge on the worksheet from bosonic strings and the S. The S is the S that I discussed here. Okay, in the target space. Yeah. But this works actually. I mean, besides the physical fields, works also for antifields and everything. Okay. So I think I'm stop here. Okay. Last lectures, I will give you information. I will discuss a little bit more about physical fields, physical subspace, let's say the physical sector of the theory. Okay. How do you recover the physical fields? How you recover gauge invariant operators? Okay. And I will show you a very nice example, which is Chern-Simons 3 dimensions, where everything works very nicely, and then you see fields, anti-fields, and then you actually there you can view this interplay between kind of worksheet operator and the operator acting on the target space. Okay. Thank you.
I understand what you're talking about here with string field theory. Yeah. I think the point that I missed is that